Okay, so the last talk today is by Dario Martelli, and he will tell us about the new index for a new black hole.
Okay, thank you. Thank you very much to the organizers for giving me the opportunity to present this work. Can you hear me? Yes? Okay. So this paper is, no? It's too far? Or?
It's working.
Maybe it's positioned too far. Is it better?
Maybe put it
closer. Closer. Yeah, but how do I do that? This way? Okay, thank you. Sorry. Okay, so this talk is based on work with various collaborators, which are named during the presentation. And it's actually mainly based on two papers, and it's roughly divided into first part where I talk about one paper and second part about the second paper. But I also mentioned two other papers that are relevant. And altogether, these four papers, I like to say that they kind of work out as I will explain, the first example of a holographic duality, which involves orbitals, both on the gravity side and on the field theory side. Now, the gravity side has been already nicely anticipated by the previous talk of Yannis. So the black hole that is referred here was already mentioned in the previous talk, but my emphasis will be completely different. I will talk about its supersymmetric properties and how it's related to the field theory dual. Okay, so that's an outline of the talk. So in interest of time, I will not give, as other speakers, I will not give technical details, so it will be more of an overview. I will start with some introduction of the topic by reminding the audience about two various ways of preserving supersymmetry, and then how this accelerating black hole fits into this scheme of ways of preserving supersymmetry. And then this will exhaust the first part. And in the second part, I will talk about how from the black hole we ended up in some field theory computation, and eventually kind of going back, this field theory computation can be used to reproduce the entropy of the black hole. Okay, so the setup in this talk, I will focus on four-dimensional asymptotically ADS4 supersymmetric black holes with three-dimensional field theory duals. Okay, so we can always think of them in some four-dimensional gauge supergravity, but also we want to be able to uplift them in 11 dimensions so that we can apply M theory and string theory to discuss the field theory dual. So this can be thought as arising from wrapping, in particular, N2 branes when we uplift to 11 dimensions on a two-dimensional surface. And here, with this word surface, I want to be vague for the moment. So it's a two-dimensional object in a way that preserves supersymmetry. If we do that, the three-dimensional field theory that we start with, for example, the ABJM theory, we can take this as the main example during this talk, is compactified down to a one-dimensional superconformal quantum mechanics. And the black hole solution can be viewed as a flow, as it's standard in holography, from the three-dimensional theory that lives at the conformal boundary and the one-dimensional theory that lives at the extremal horizon, where an ADS2 trough is developed. Much of what I will discuss have higher dimensional analogs. So this is just an advertisement, so to say. But I will focus on ADS4 and CFT3. Okay, so first way to preserve supersymmetry, it's quite well known, but let me quickly go through that. So one can quite schematically couple your theory that we wanted to think as compactifying on a two-dimensional surface, as I said. And here let's think about the Riemann surface to be specific with genus G. So you couple this theory to an external gauge field, and we call it an R-symmetry gauge field because it's going to appear in the Killing-Spinner equation of the theory exactly in this form here. And then by just identifying this gauge field with essentially the spin connection on the Riemann surface, supersymmetry is simply preserved by taking the spinors to be constant, and therefore this is known as a twist, a topological twist, because the spinor becomes effectively a scalar. A little bit more geometrically, this gauge field is a connection on a line bundle that gets identified with the tangent bundle of the Riemann surface. So through this chain of identities, one can see that the constraint that the flux of this gauge field has to satisfy has to be given by this number here, which involves the genus of the Riemann surface. So let me draw your attention that for G equals 0, that is the two-sphere, then this number has to be equal to 2 in my conventions, which are the standard conventions. So for G equals 0, again, for this two-sphere, supersymmetry can also be preserved in a different way, and perhaps is a more standard, more traditional way, if you want, because, as is well known, on any sphere in any dimension, there exist Killing spinors that obey this equation here. And in this case, there is no need to add any background gauge field, A. So I will refer to this as a sort of a no-twist condition, but still supersymmetry, of course, is preserved. A little bit more generally, one can still couple the theory to a number of different gauge fields for various U1 symmetries in a way that then the sort of the Killing spinor is uncharged, and so under a combination which we can take for convenience to be the diagonal one, right? So essentially, we take the R symmetry to be 0 if we want to preserve this in this way. So if I state that at the level of the integral of the fluxes, which I will refer to them as fluxes themselves, so these are integers, these and I. You can think of them as magnetic charges, if you want, they're the same thing. The topological twist is a constraint that says that the sum of these magnetic charges has to be this number here, whereas in this other case of no twist, it has to be 0. These two very general ways of preserving supersymmetry can be implemented either in the field theory or in gravity, supergravity. And if we do that in the specific case of interest for us, which is four-dimensional supergravity, then the two mechanisms to preserve supersymmetry are realized by well-known supersymmetric black holes. The one class is so-called topologically twisted black hole, which is a static and magnetically charged black hole due to, I guess, Cacciatore and Clem originally. And then the other class, which is sort of orthogonal to that, to the previous one, are the Kerr-Newman, which are rotating, and they are, in general, dionically charged, so they have both electric and magnetic charges. And in the context of supergravity, I guess they were found by Gibbons and collaborators. Now, the details of these two classes of black holes differ, of course. One class rotates, the other doesn't, and so on. But in all cases, the entropy, which is the main observable of interest, I would say, for a black hole, and here by entropy I mean really 1/4 of the area of the horizon, is a function. Once you have the solution, your parameters, as Yanis was describing, and then you compute it one way or another, and you get a function of these magnetic charges. And of course, in the case that there are also electric charges, there will be also a function of the electric charges. But I want to focus on the dependence of these magnetic charges here. So the challenge is then to reproduce this entropy from a microscopic computation using holography. So this is the challenge for holography and for whoever is interested in understanding microscopically the entropy of the black hole. The key ingredients for resolving this challenge are given in like a 4-step procedure. You have to identify the dual field theories by looking at the internal geometry. And this is a step which is trivial today. We can always think of the internal geometry being S7, and so we have ABGM theory, so that's not important today. Then you have to identify the three-dimensional background from the conformal boundary. And for that, we had already an appetizer from the previous talk that this can be an extremely challenging task, at least at technical level. Even more challenging, once you have identified this conformal boundary geometry, you have to compute the partition function in that background using presumably localization or any other method if you know a better one. And then finally, once you solve this at the third point, there is still much work to do because you have to compute basically you have to do some limit, typically a large n limit or some card limit as well. And then you have to compute this matrix model and finally extremise it and get the entropy. So that procedure here you can think as to be applied in these two cases. It has been applied successfully, and there is a famous match for both cases. Now, let's move on to the main object of interest for this talk today, the main novelty. In a couple of papers here about already 4 years ago with these collaborators, we proposed that p-branes in general, let's say, can be wrapped on a spindle, which is this object here, which appeared already in the previous talk. So the wedged projective line with two singularities, orbifold singularities at the north and south poles. And therefore, this, in principle, is supposed to extend the ADS-CFT correspondence to a much broader class of situations where both in gravity as well as in field theory, you have this orbifold here. And then, as we will allude later, in fact, not only later we have people, including myself and many other authors, have extended this proposal for higher dimensional orbifolds as well. Okay. So then if you have a p-brane and you wrap it on this two-dimensional orbifold, which we will call spindle, then you get an effective theory in p plus 1 dimensions. And this works for any p, but for p equal 2, which is the focus today for M2 branes, then you get effectively a 1 plus 0 dimensional theory, which is, as I said, a quantum mechanics. And if there is a solution which is an ADS2 throat, then you might think that that's super conformal. Now, some new features, some slides for discussing condensing the new features of the spindles, besides the obvious one. Here is a list. So it does not admit metric with constant curvature. It is a bad orbifold, which plays an important role. It means it's not a quotient of a quotient by some discrete group of a manifold, like the typical orbifolds T, some torus models at Zn, etc. And it has also a U1 symmetry, which is the rotation along the azimuthal axis. And the most striking feature, perhaps, is that one can show, and it has been shown in this paper here, that supersymmetry can be preserved in only two ways. So it can be preserved by coupling to a number of external, quite generally, I mean, in an arbitrary, let's say, theory which admits Killing spinners, to an arbitrary number of flavor gauge fields, provided they obey this constraint here, which involves the choice of two signs. So these sigma 1 and sigma 2 are plus or minus 1s, and in fact, only their product is really meaningful, right? So only the relative sign. So essentially, there are two ways, and they depend on the sign of this sigma, which is either plus or minus 1, and these two ways have been called twist and anti-twist. Now, for sigma equal plus 1, you can see that this is what you get. And in particular, if you set n plus and n minus equal to 1, and you go back to the sphere, you get number 2, which I already showed previously. So for that reason, this is called topological twist, or more briefly, just twist. Whereas for sigma equal to minus 1, then in this particular case, that reduces to the situation where you had no twist. You had 0 on this side. And that, for this reason, it has been called anti-twist. Just a check on the time to be... What? More, 11 minutes. Okay, good. I'll speed up a little bit. Okay, so now what it turns out is that, in fact, one can implement these twists and anti-twists on the spindle precisely in the situation where you have these accelerating black holes, which have been mentioned already, right? So they are rotating, they have a magnetic and electric charge, and the horizon is precisely a spindle, and you can see this spindle also at the asymptotic boundary where you get spindle times S1 in the kind of compactified situation. And in the minimal theory, it is realized, so in the minimal gauge supergravity, only this anti-twist is realized, right, with sign +1, but actually one can show that in more general situations, one can also realize the other sign. So generically speaking, one can realize for these accelerating black holes either the twist or the anti-twist. Okay, now, by doing some computations which were completely oblivious to the new progress that has been reported today, we managed, in this paper here, a couple of years ago, to compute some features of the thermodynamics by following a procedure which was actually reviewed in a talk today in the parallel session by Vasil Dimitrov. So by using a procedure of deforming the solution to a complex and supersymmetric but non-extremal, one can compute this on-shell action, which depends on these chemical potentials or fugacities, little phi for the electric charge and epsilon for the angular momentum. Chi here denotes the Euler orbifold characteristics of the spindle, which is this number here, right? So this can be further written in terms of these gravitational blocks here, these basic building blocks, and this plays a role eventually if we get to that point. Now, extremizing this function here, namely doing the Legendre transform, and further imposing that you get on a real slice, one reproduces the black hole entropy. So this is like a third way to get the black hole entropy, which is not just computing the area of the horizon, of course, but it's still a gravitational way. So I'm interested in finding this from an independent field theory computation. Okay, so here is the second part of the talk, which I'll go a little bit more quickly, perhaps. So we want to reproduce this entropy, which was flashed in the last slide, by a microscopic computation of the partition function of the dual CFT, which we can take ABGM, as I said, if we want, on the background geometry, which is topologically the spindle times S1. Now, this background, as was flashed in the previous talk, has an extremely complicated metric. And I guess this was not reported, so I'm reporting it here. This is the background gauge field, which is also extremely complicated. And it depends on a number of parameters, which are constrained by some supersymmetry conditions. So that leaves, in the end, only two independent parameters. So it's quite complicated, but we have to think about its qualitative features. It has conical orbifold singularities at the poles. It has a complex metric, which is inherited from the bulk analysis of the previous slide. And the gauge field obeys this particular anti-twist condition. So before attempting to implement localization of the ABGM model on this background, we need to tame these features, which were not incorporated in previous analysis. And this was done in this second paper, which I mentioned in the first slide. So the complexified rigid background does not fit in previous analysis, where the metric was assumed to be real. So we basically redid the analysis from scratch by assuming that the metric can be complex. So we had to, in this paper here, we analyzed the most general Euclidean complex background admitting two Keening spinors of new minimal supergravity in 3 dimensions. So that's the Keening spinor equations. And that was done by following in a way, the standard procedure of looking at the bilinears, but with some care in not involving bilinears which involves like the complex conjugate. So we kind of use some holomorphic, in quote marks, variables. And that's actually a very general procedure that can be applied in other situations. We are working on some other related follow-ups in different dimensions, etc. The outcome of the analysis is that one gets a complex Killing vector, which is parameterized entirely by this complex constant, which is now here reported in red, this omega. And then the most general metric can be written in this form. It's a three-dimensional metric because it's a three-dimensional theory. And then, without looking at the details, of course, which are not very important, one can work out the explicit expressions of all these bilinears. That's the one form. These are two other one forms. So this is this K with P plus and P minus. They represent a sort of a canonical complex frame for the complex metric. Right? So here by complex, I really mean that the entries are complex valued. I don't mean like Hermitian. Right? It's some sort of non-standard thing. You would not find this discussed, I guess, in any mathematical paper or book. Okay, so the analysis is completed by working out the explicit expressions of the background fields. And that's very general. Then you have to start imposing some boundary conditions. So you have to impose that one coordinate is the coordinates on S1, and the remaining two coordinates are coordinates on the spindle. And imposing boundary conditions, it means you want to make sure that this is a smooth metric and with smooth background fields. Once you have done that, there is no more freedom, so you have to take your background and check what is the flux of the base, and it turns out that it obeys this expression here. So it is exactly of the two possible forms that are guaranteed by the general analysis, right? So depending on these signs, so this S plus and S minus are signs, one can realize either the twist or the anti-twist. So in a way, supersymmetry knows already that this is what you can get, and this is in fact exactly what we get. Now, the boundary of the accelerating black hole, which, as I said, is quite complicated, fits into this general framework. It's explicitly checked. And we could start doing the localization procedure. However, this is since the final result does not depend on the details of the background, but only on some very rough details, let's say. In particular, it depends only on this parameter omega. Then we can consider simpler backgrounds as reference for presentational reasons or for performing the intermediate computations. For example, like this one, right? So this is, roughly speaking, you can recognize there is like a sort of a two-dimensional part, which is the spindle. There could be also the two-sphere in particular case, and then there is the S1 part, and there is this vibration term, which represents a sort of rotation, indeed, right? Now, the two cases in this simple background are then boiled down to two sort of constraints on the parameters of the solutions. So you can really take these capital omega and beta to be real constant, and you can realize the twist and the anti-twist in these two ways. Now, if you set n plus and n minus to 1 in this previous background, then this reduces to S1 cross S2 with this twisting, with the rotation but no twist. Or in the other case, for the other type of supersymmetry preservation, to the standard topological twist. So as a check on the calculation, in these limits, one must recover the superconformal index, which is known to come from localization on this background, or the topologically twisted index, which comes from this second background. So the partition function in this background defines two new indices, which one can call the anti-twisted spindle index and the twisted spindle index. But in fact, in the paper, we obtained more than what we hoped for. And in fact, we could obtain a single formula that incorporates both these. And we call this the spindle index. All right? So this unified the previously known indices and generalized it to the case of the spindle. Now, okay, the localization. Okay, I will definitely have to skip some many details. But the punchline of the localization is that one can follow one's nose, so follow basically the strategy outlined by Pestun, and though the modifications were needed. So one can start by reformulating the problem in this cohomological form, and then One is reduced to finding just some subset of the eigenvalues. So these are called the unpaired modes. And you can do this thing in two ways. Either by taking a simple ansatz and analyzing the boundary conditions, which leads to some constraint on these integers, which importantly involve these fractional parts of these rational numbers here. And this is, in fact, actually one point to pause a little bit, because these integer parts or floor functions are the new distinctive features associated with orbifolds, which also appeared in other mathematical literature where people studied like enumerative invariants on orbifolds and so on. And they are the main technical complication, also in the context of the Largen limit, which I will mention later maybe. Okay, so one can go on and then produce the final matrix model in terms of Pocamer symbols and get an explicit matrix model. Now, the same computation can be done also in a different and perhaps more elegant way by using the equivariant orbifold index theorem, where one can show that the same result is obtained by picking up fixed point contribution from the north and the south poles. And the two results exactly match, which is a check on the computation itself. Okay? So let me conclude. I'll skip the Chern-Simon part. So the last thing I want to say is that once you have obtained this matrix model, then one can go on and study the Largen limit. And there are also some follow-up other papers that we are working on. But instead of going too much over time, I certainly refer the interested people to a talk by Eduardo Colombo, who is here, one of the authors of this paper. On Thursday, in a parallel session, we'll discuss this Largen limit of this spindle index. And the upshot is that the Largen limit of the spindle index, which will be discussed by Eduardo, reproduces this entropy function, and as a result, it reproduces the entropy of the accelerating black hole. Okay, so just to conclude, the story here is that we have started from the accelerating black hole and then went to the localization computation, passing through some revision of the kind of background supersymmetry. And from that, finally, and that's the reason why I am happy to discuss this today, is that we also obtained the microstate of the black hole from the larger limit by closing this loop. And this then represents, as I said at the beginning, the first example of an orbifold holography that has been completed. Many other extensions are underway. In four-dimensional gravity, a paper will appear soon. Actually, a couple of different papers. And for this paper, also, I want to mention that Alessio Fontana Rossa is my student, and he's going to talk on Thursday again. So this is for some different application of the same kind of themes. And there are many other directions that one can pursue. For example, a look at subleading corrections. We only looked at the leading order, like n to the 3/2 scaling, but one can hope to extend some work by Nicolai and collaborators. Also look at many other branes, not only M2 branes, but other types of branes. And also, as I also mentioned at some point, higher dimensional orbifolds. So higher than 2, the spindle has dimension 2, but you can take 4-dimensional orbifolds or possibly higher dimensional orbifolds as well. So the last thing I want to say is that supersymmetric field theories on orbifolds, I believe they promise to lead to several interesting new features and surprises, and looking at them through holography is, for me, the best way to try to approach this problem. Thank you very much.
Thank you very much. Any questions?
Sorry, so I also didn't mention that, right? I mean, so you know that, like, depending on the value of the acceleration relative to the ADS horizon, right? I mean, there are kind of different properties, right? I mean, so there's this weak acceleration limit, right? I mean, then if it's bigger than that limit, then you have actually two accelerating black holes.
Yeah.
So I was just wondering whether this plays a role, like, I mean, in this analysis, like in the supersymmetric.
No, in the analysis, we assume that we are in this week where you have only one horizon. So we did not do anything about this, the more complicated situation, which is certainly, I mean, this is already complicated enough, but certainly it's just something interesting to possibly explore. Yeah.
I wanted to ask, is there, do you have any comments or insights on how you would go about doing something similar for the case of spindles in 5D supergravity?
I have an upcoming paper, but yeah, it's with the same collaborators, with the same set of collaborators, we have worked on various four-dimensional orbifolds, which involve the spindle as well, and they define again like new indices in 4 dimensions, which generalize previous indices, and from those modulo various technical complications, which after the summer we should streamline. From those, it should be possible to extract, for example, the central charge of the dual gravitational theory, which is like ADS3 times the spindle, for example.
Okay, well, I know that there was some debate about how you could implement the anti-twist on the boundary.
Yeah, this is a very, I mean, this is like a sort of a comment from an expert. Indeed, it's very tricky. We are addressing this in this work. I can say that at the moment there isn't a completely satisfactory answer. There are some answers. And the answers arise from doing this very general analysis of supersymmetry in a rigid background with complex metric. Yeah, and then in a way we cornered this. We don't have something as nice as in 3 dimensions, but there is something. I'm happy to talk if you want more.
The final question on here.
Yeah. Thanks for this nice talk here.
Oh,
yeah. Do you have an understanding of what is acceleration from the CFD perspective? What is the meaning? What do you do in the CFD?
Not of the acceleration by itself. The only understanding, which is again still in progress, progressing, is that you're supposed to take your field theory and put it on an orbifold. I don't see any acceleration as it is in the context of the field theory.
Maybe a related question. I mean, you counted the states and you got the right number. Do you have a more detailed understanding which state you're counting?
That's also another very good question, which perhaps is simpler eventually to answer. I don't have a good understanding because the part which I really skipped because of lack of time, we sort of computed this by following our nose and then getting a result that passes various checks, including some dualities and especially the large n limit for the microstates, etc. We didn't approach that from the microscopic point of view of, like in the old days, people would say, oh, let's count all the possible operators, which is what you're asking. I think that should involve counting some sort of fractional instantons or vortices, but these are just buzzwords which need to be made solid. I had some discussions with people, for example, with Alessandro Tanzini, the experts on this counting of these things, and that seems to be possibly what should be the case, but it's something which we haven't thought about.
Okay, thank you. That concludes the session. Let's thank Dario again.